Szybko, szybko! Szybko, szybko!
Hello, welcome everybody. We are quarter past 1, so I guess we can start. Welcome, my name is Maciej. I was a member of PW Racing Team for 4 years, during which I took part in 10 competitions and took part also in a lot of scrutineering. So yeah, currently I'm working in Radiotechnica marketing. Our company is an expert in electronics and electrical system research and development. We also have a quite advanced EMC laboratory that we are really proud of. A topic of today's presentation will be design of Formula Student electronics for rules compliance, because I think it's a quite crucial step for every EV team to have a rules compliant car. It's like a basis of everything. So yeah, we'll delve more into this. And yeah, also a few remarks that will not delve too deep because there's too much technicalities, of course. And also I want to say that the most active members will be rewarded at the end of presentation, so feel free to take part. All right. Oh, 1 second. Sorry for that, some technical issues. Okay, so a few preliminary information at the beginning. Next click, please. There is no single solution, yes. When it comes to developing electronics, there is a lot of stuff to take into account. There is no like single universal solution for every problem. So don't like focus on one single solution you solve somewhere, because as there is in the next point, please next point. Solutions depends on your system architecture. So it has to be, you have to be you have to know that the system has to work as a whole on your car. So it's really important to take this into an account, that some solutions depend on the systems you developed earlier. So take this into account when developing something in the future. Also, next. What matters most is the functionality and the implementation, of course, as long as it's rules compliance. So, for example, during first years of EV cars, you may come into a problem where you overcomplicate things and yeah, create problems for yourself. But if it's working, that's all right. You can simplify it in the future. As mentioned in the next point, keep it simple. So if you know something is working and you can optimize it, make it simpler, trust me, it will be easier for you and also for the scrutineers that will have to like understand your system and also what you developed. All right, so going further, a very crucial part of this presentation is, of course, the documents, because let's be honest, I've built and you're building cars based on these regulations. So it's really important to like have a good knowledge of the regulations, especially FSG Formula Student rules, or of course specific competitions handbook. So it's really important to have them in mind. Also, a next thing is competitions inspection sheets. So this is like the guidance for scrutineers how to judge your car if it's safe. So it's really important to take an inspection sheet in your garage, print it out, and make sure that you at least comply with the points written in the inspection sheet. Also, competitions handbook. A lot of really important stuff is written there, especially about the data logger, how to store your battery, and all this stuff. So it's really important that you do not gain like a penalty for that, because every point matters, of course, in Formula Student. It's really important to keep this in mind. And yeah, next. That's quite a, I would say, you would not think it would be here, but Reddit has a space for SciA members and also for most students. And it's really important because there's a lot of knowledge hidden there and also a lot of technicalities discussed there. So if you have a question, you can always ask your question and you will get an answer from more experienced team members, even from another country. And yeah, you will always find something useful there. You can always ask. Okay, so let's delve further into subsystems we'll discuss today. So I switched it to two categories, basically. The one is low voltage part of the system, but it also influences the car. And the other one is the tractive system part of the car. So going further from the low voltage side, of course, we have shutdown circuit, BSPD, APPS, and AMS and IMD. From the high voltage side, we have T-cell logic, and as an indicator, voltage indicator, discharge and pre-charge modules. Okay, going further. Let's start with the low voltage part of the car. All right, so let's start with the shutdown circuit, which is, of course, the backbone of the car, which is responsible for power supply of most crucial parts of the car. And yeah, what matters here most is that in the rule book, there is a basic schematic, an example of an implementation. And it's really important to make use of that because it shows the basic architecture. And then, of course, you can adjust some things to your needs. But it's really important to keep in mind the whole architecture of it. So, for example, the place of the TSMS, where it should be placed, the order of things. And yeah, regarding also shutdown circuit, if you, for example, have motors in wheel hubs, it's really important to also have the additional interlocks on shorter suspension member as well as high voltage wiring. And what's also important is that every tractive system connector has to have a dedicated interlock in it. So keep it in mind, and also it will spare you a lot of time during scrutineering, trust me. And yeah, we can go further to BSPD, which is, I would say, yeah, kind of crucial. What's also kind of, it's a, I would say, like a testament to the fact that even the best teams have problems with this part. During FSG this year, 2 teams were disqualified for BSPD from endurance. So yeah, it really matters to have a rules compliant BSPD, and we will delve more into the technicalities of it. So according to rules, the BSPD is required to monitor, of course, TS current, which relates to power delivered to the motor, and it's also relative to maximum tractive system voltage, of course. So maximum tractive system voltage multiplied by the output of the current sensor, and we have the power, of course. Then we have brake pressure, but it's not specified how the signal should be. It is specified below 30 bars, and of course no locked wheels. So this is the monitoring stuff. And then we have the timers mentioned in the rule book. So we have the persistence of signals. So if both of them are triggered for more than half a second, we have to take an action. And then the reset time of the BSPD, which was also the clue of the disqualifying of the teams. So going further, yeah, it's also important to notice that both signals are SCSs, so system critical signals, and it's very important to keep it in mind because during inspection, it's really checked, and you have to simulate a short to ground or open wire. So it's really important to have the subsystems in your modules that you are not worried during inspection that something is not rule compliant. And yeah, going further, here, for example, we have one implementation of it, how it can be implemented. So basically, for every sensor, we have 2 functionalities. So checking if the threshold is crossed, and the other one is checking for short circuit for supply, ground, or open wire. It's really important to have pull downs of signals on dedicated modules. So when you have an open wire problem, you don't have a floating input, because it's really problematic, especially with electric car, when you can have some EMI issues and stuff like this. So we have the trigger block, which is responsible then for driving the logic and basically checking if the two signals are present, and also fault, which checks for faults in the wiring, of course. And then we have also the delay block, which is responsible for checking if the persistence is more than half a second, and also for the reset of the BSPD, which is 10 seconds, of course. And then we have the action of the shutdown circuit, which is opening it or being able to close it again. Going further, APPS, which is also a crucial part of the electric car, but we'll more focus on analog sensors, which is a more simpler solution, I would say. Most important, I mean, the most, I would say, the easiest solution would be to use a potentiometer, a linear one, for example. And also, few things to keep in mind is that two sensors has to be used. Of course, both signals are SESs because they influence the car and the tractive system itself. In case of analog sensor, non-intersecting transfer functions. And I will delve into this in just a second. And in case of implausibility, torque should be cut off from the motor. So, also important thing to keep in mind is that to have photos prepared, of course, of return of the APPS pedal with one spring, and this is, for example, like a basic implementation of it. So we have two linear potentiometers with different supply voltages. This is like a one way to do it. But of course you can implement it in many ways. So this is like a basic one, I would say. So going further. This is like whole points on its own, but it doesn't have like a dedicated one point like BSPD in the rules. But I think it's very important to mention it because in the rule book there is a lot of single rules specifying how the AMS and IMD should be triggered in case of a failure. So I thought it would be easier to make it as a one unit. So we are monitoring for AMS and IMD failures, and we are acting accordingly. Also, it influences the indicator in the cockpit. So as specified in the rules, we have the indicator for AMS, which is red. Also, next point, please. Of course, there are SCSs. The same stuff for the IMD, and it's also a SCS. So we can go to the block diagram. Here's like a basic block diagram of this subcircuit, let's say. How you can implement it is one way. Of course, you can do it the other way. Also, it's important to notice that it has to be non-programmable logic, like the T-cell. Also important part is that it should be resetted by the button on the side of the car, not accessible to the driver. It's also checked very, very often during scrutineering. As you know, every IMD test, which is done like almost every time you're entering dynamic area. So it's very good to have it implemented properly, that you're not having problems later on. So here we have like a basic architecture where we are monitoring IMD and AMS states. We have a latch logic, and of course the driver which drives the indicator itself, which is located in the cockpit. Going further, tractive system. And here are the modules, hardware, which is the most commonly developed by the teams, and which is required by the rules, of course. So yeah, T-cell. We have two indicators basically. We have the green one and also the red one. The green one is influenced by the state of iris, and of course the state of the preacher relay. And also we are monitoring voltage after the iris in the battery. And this is one subsystem of T-cell which is required by the rules. Also with the red indicator that just measures the DC link voltage. Then we are driving the both indicators accordingly, but they are independent systems. Also, it's very important to mention that they are hardwired electronics and all signals are SCSs. So yeah, going to diagram. Here is, for example, like one implementation of it when we are monitoring signals and we are also checking for faults. And yeah, we're driving logic according to the signals. And independently, we have the driver which drives the red indicator by monitoring the high voltage part of the car. Yeah, switching next to pre-charge system. Yeah, the implementation of pre-charge in the rules is not really specified. It can be programmable, non-programmable. The most crucial part is the functionality. Because trust me, like stacking your iris is not a cool thing. A lot of problems with it. So yeah, it ensures the pre-charge state of DC link before closing the IR plus. Yeah, also the relay is specified, and the power rating of the pre-charge resistor is really important because always checked during inspection. So make sure that everything is done correctly. And yeah, going further. So yeah, here's like a very basic representation of it. So we have two relays in the battery, of course. We have the pre-charge relay, and it's driven by the shutdown circuit, which is also optional, but it simplifies things. Going further, we have the voltage indicator, which is also specified by the rules, and also a very important part of the battery inspection. So yeah, it's basically like a, let's say, warning light in case something goes wrong with the battery. It also shows that the battery is supplying the tractive system. And yeah, it's really important to keep in mind the threshold voltage of the module, which is below 60 volt. And yeah, no software control is allowed, and it has to be supplied from the tractive system and also self-sufficient. So basically, it has to be on even without the low voltage system present on the car or in the battery. So yeah, one way to do it is like a, for example, constant current source located in the battery, or you can do, for example, like a converter, for example, like a flyback converter. Okay, going further, we have the discharge. Oh, here is also the schematic. It has to be connected on the vehicle side of the car after iris. And yeah, going further into discharge. Yeah, it's very important to prove to the scrutineers that the module is able to handle tractive system voltage permanently. Also, the path cannot be fused. Also, another important part is that it's a one way to say it, but you can very simply implement the turn-on capability of discharge module by simply negating the driving the SDC. So basically, if you're powering the airs, you're not powering the discharge, and in other way around. But it's really important to keep in mind that it has to be normally closed. Yeah, also proper power rating, and in some cases proper power dissipation, which is also required to fulfill the ability to survive, let's say, non-stop connection. So yeah, here's like a final schematic of the connections. Okay, we can go further. And yeah, very important things to keep in mind during PCB's development, especially the one containing tractive system voltage on it. So also, when you're picking components, it's very important that the test voltage is proper that it's the one specified in the rules, and it's also compliant with your maximum tractive system voltage. Also, the time of the test is important. Isolation barrier is also important, and it's also checked during inspection. So yeah, going further. Except for the interlock, of course. So no connector with both TS and low voltage, except for the interlock in the connector. Mark areas of the PCB with tractive system, low voltage. It's really easier for the scrutineers than to check the rules compliance. Also keep in mind that it's a cool feature, I would say, and it also spares time when you're specifying the spacing of both parts. So for example, like additional label saying 4 millimeters of spacing with an arrows between the two lines, for example. And yeah, conformal coating. It's really important to use conformal coating according to the datasheet, which is also specified in the inspection sheet, and scrutineers always ask about this. Remember to clean the board, and yeah, that the process is properly conducted. Yeah, also a very important thing, if something is not accessible, be prepared with spare board. It's also specified in the rules, but it's also important to keep in mind that even if something is hard to reach, it's always best to have like a spare, show it to the scrutineer, and it will spare a lot of time. Okay, going further. Yeah, some useful remarks regarding the overall system and yeah, practices. As much photos as possible. It really spares time when you're unable to show some, for example, some enclosure or something that is not easily accessible. When you have a photo, it's really easy for you to show it and for the scrutineer to see it, so you're both not wasting a lot of time. Yeah, it's when you're showing a photo, a proper photo of the enclosure, it's generally not an issue to not open. And yeah, then yeah, study inspection sheets. It's really a lifesaver when you have an opportunity to check your car, the compliance of it with the inspection sheet. The inspection sheets are published like a month, 2 months before the competition, so you have a lot of time to study it and make sure that you're ready for the proper for the true scrutineering. And next. Yeah, and also be prepared with the equipment. So all the custom tools, all the tools specified in the inspection sheet, especially for the electrical and battery scrutineering. Also important to keep all the documentation with you in a digital or printed form. Really a lifesaver to have a ESF, FSG ESF site open on your computer. It's really easier for you to show to someone, and yeah, also you can spare a lot of time. And it's really important to spare as much time as possible, so you'll make it in your slot. Also, you can prepare a lot of tools which are really useful during scrutineering, where you can make sure that you're that you can show to the scrutineer how your car is rules compliance. So, for example, like a dedicated connector to supply some, for example, voltage indicator, or have like a dedicated connector with an interlock to override the HVD interlock during, for example, TSL check during scrutineering. Also the BSPD test circuit to make sure that you're ready to show the scrutineer that your car, the BSPD is rules compliance. So yeah. And that will be all. Thank you very much. And if you have some questions, this is the time. Yes? Okay, so the most important, for the PCB, of course. Yeah, for the PCB. The most important ones are the one providing the insulation between low voltage and tractive system. So for example, if you have an optocoupler, for sure you'll be asked to provide this data sheet. Yeah. What else? For example, if you have a, I don't know, a connector through which is routed, I mean the PCB connector, through which is routed tractive system, it also have to have proper rating. So basically all, for sure, stuff that contains tractive system. Any other questions? Don't be scared. It's not scrutineering. So. Yeah, special award for an active member. Yeah, please. When both signals are triggered. So when you are supplying more than 5 kilowatts, and when the hard braking occurs, and after 500 milliseconds, you should be able, you should open the SDC. Can you repeat?
Yes, in the electric car are very simple. On combustion car, we have a problem with the BSPD system because if you keep the pedal pressed, because on the combustion it's more simple. If you press the brake and throttle in the same time for more than 500 milliseconds, the BSPD will goes down your old circuits, shutdown circuits. And if you are keeping the pedals in the same position, um, your BSPD needs to stay down. The question is, what is the time or when needs to start the timing for BSPD? For the reset, yes.
If the both signals are not present.
After,
For example, if you trigger BSPD,
yes.
and then, for example, for 2 seconds, the signals are still there, and after, so basically, if you trigger the BSPD, and the signals are still present, for example, for 2 seconds, for example, a time for the driver to put the pedal up, so it's not a trigger anymore. So you have the time to trigger BSPD. 2 seconds is when you are not start counting, and then just after these 2 seconds where there is no signals present, you can start reset time. Uh, Let me specify it. You're waiting 10 seconds after there are no signals present. 2 seconds plus. So for example, if the driver, one driver is pressing for 2 extra seconds, the other one for 15, the time would be 12 or 15. Yeah. You're welcome. Any other questions? Yeah, sure.
Over 600 volts. Uh, um, Last season we were doing this using MOSFET. We were driving the LED with a MOSFET, and it was overheating. Do you have any suggestions to stop the MOSFET from overheating? Use 2 MOSFETs would be a solution?
It depends, because it's not maybe a good solution, because one can overheat and will take more current, for example, than the other one. or in the other way around. So the best approach would be to provide a proper heat dissipation. That's one thing, or come up with maybe a solution that is not so that is not dissipating a lot of power. So, for example, there are some dedicated DC-DC converters for this, for like this application. This is one solution, or maybe provide a better heat dissipation. So maybe thermal paste, some heat sink, do the maths, and yeah.
Okay, thank you.
Can you give the microphone? Thank you.
Okay, you said that you're also specialized in EMC. Do you have? Okay.
It's hard to say it,
okay.
even if you're working for 10 years.
Yeah, yeah, EMC is hard. Do you have some EMC test recommendations for electric vehicles?
All right. So, okay, compatibility for Formula Standard car, I would say it's like not needed. The stuff you should be worried about is like if the car is working properly, because if you're losing some functionalities because of the interference, this is the stuff you should be worried about. Because compatibility is like up to the standard, for example. So if you're asking me about how to make sure that your car is not like turning off, for example, or like having problems during driving, there are some general techniques for this. It's really hard to have like a general guidance. It really depends. For example, if you route a wiring harness near your inverter box and you route it like this way or this way, it may really differ.
It matters. Yeah, it matters.
Yes, yes. Also, if you want to do some testing, like on a bench, let's say,
Yeah.
you can, for example, you can create your own like near field probes. I don't know if you've heard about this.
Yeah, I heard about it. We didn't use it, do it, but I read about it. So the best way is to just build the car and test on the working car.
Yeah, if you have a problem, for example, I don't know, with some signal, measure it, define the problem. You can using, for example, a near field probe for magnetic radiation. You can determine if it's a, for example, like a voltage is inducing in the wire, maybe some current is flowing, and this way you can determine it, because it's really depends on the problem itself, how you will solve it. If it's, for example, induced voltage in a wire, or if it's a current flowing through a wire. Also, there's like different types of this radiation. So you have to act accordingly.
Yeah, so we don't recommend testing each board for EMC separately for immunity.
You mean like a proper testing in a lab? I mean, I'd say if you have time to do it, why not? If you have capabilities and time, you can try. You will learn something from that, and this is important. As it is in Formula Student, that you will learn. But for the sake of like functionality or something like this, I don't think it's really that important. Compliance, like compatibility. Sorry, I would say that the functionality of the car and that it's not having an issue. For example, that the indicator is glowing up or something like this because of some current going through another way. It's not that required.
Okay. Thank you.
No problem. Any other questions?
What are some tips would you give me when starting developing the BMS system?
BMS.
Yes, yes.
Oh, it's not a coincidence that it's not shown here, because it's a topic on its own. It's really an advanced topic, but what I would suggest is start small, make sure that you have a proper team, at least 2 members for hardware, two members for software. Be consistent, work all around the season. Do not take breaks from the project. I would start, for example, with like a slave board and one master board, and establish communication between them, make sure that the slave is working, and then you can like make it bigger as the times go on. So make sure that you simplify the whole design process into steps, and then make these small steps. In the end, you will have a whole project. This is how I would approach it.
Okay, thank you.
Please.
During the design of an EV harness, what rules would you like take for choosing which wires to have shielded?
During design of high voltage wiring harness?
Also low voltage.
Low voltage. And if it should be shielded?
Yes.
Okay, so what I really recommend, of course it's also required by the rules, that all tracking system wires running out of the enclosure should be shielded. That's one thing. For another, I would say for low voltage, depends how the harness will be routed. But when you're, for example, making the wiring harness, make sure that I don't know what communication protocol you're using, but for some I would suggest shielded cables. For example, for like a CAN communication, twisted pair shielded cable. And yeah, make sure that the shield is connected to ground, but do not create ground loops, because it's really have an impact then during testing, for example, or that some current is flowing through the shield. Generally, when I was in the team, we had a rule that high voltage shields would be connected from 2 sides, low voltage just on 1 side. And also make sure that you have like one common ground spot, for example, main hub, so you don't have loops between your grounds. I don't know if I answered your question. Maybe something you want to add? Okay, thank you. Right, someone else, maybe? Green soundtrack. All right, then thank you very much for attendance. And yeah, if you have some questions, you can find us at Radiotechnica marketing stand, and we'll also provide some blankets, very warm ones, later that day. So be there at time.
Is someone still have doubts about your cars or have inconsistency in your design? Just go back to our tent, and we will take the discussions. And yeah.
Okay, thank you very much
for be present on this presentation.
Stop that. Stop that. Yeah, I hear him chatting the noise, move too quick, can't stop for the talking. I hear him chat with the boys, man so tough, but let's keep walking. Just too sharp with the prize, white girls let it tell me I'm awesome. Yeah, hot like fire